Bismillah Rahman Rahim. Assalamu alaikum. Dear students, today we will study about the neutron activation analysis again. As you know, we have studied neutron activation analysis, the principle and instrumentation, and what type of different factors that may affect the neutron activation analysis. We also have studied. Now today I would like to again start from principle of activation analysis so that we can reach at some particular points that I would like to share with you so that you can uh, get your complete concept about the principle as well as the neutron activation analysis process. As you know, you have studied in the previous lectures, and today I would also uh, give you some more information about different factors. So in order to study the activation analysis, we just go through the previous few points. First of all, that we have studied that there are some desirable features for the activation analysis, that are the rapidity of analysis, and because the process is very active and rapid in order to analyze different sample materials. The second thing is that the insensitivity to chemical form of element. And so you can say that there is no sensitivity for different elements, because any element that you would like to analyze with the help of activation analysis, you can do. The third one is the non-destructive nature of this process. The fourth one is the highly sensitive if a large particle flux is available, so that if there is a sample material, sample contents are very low, even in microgram or part per billion level, they can easily detected by the help of activation analysis. The fifth point is was that the availability of a single for automatic recording of signal for the automatic recording of results. So there are availability of signals. If there is a process of analysis was completed, it gives you some signals as well as some other form of signals that are required during the process of activation analysis and analysis of different elements. So this is the point that are actually associated with the activation analysis. The sixth one is the equipment requirement may be relatively inexpensive. So definitely, once you make some construct some type of equipment for this, and later on you would be able to get more and more analysis. So this is almost all features. This feature almost related to all type of instrument. Once you have to pay, and rest of the life, if you care for your instrument, you can easily use it for a long time. So you also have studied about the activation analysis requires us consideration of the law governing growth and decay in radioactivations. So it would be like that you have studied in previous lectures. However, I would like to go through all these things again to some extent, and then I will reach at my particular point. So there is a n number of particles and number of elements that you would like, and number of atoms that you would like to activate in some in a few time at which you want to bombard the sample material with the help of neutrons. So you will get some kind of lambda n equation that will give you the decay constant as well as the number of elements that are actually activated during this process. So there are different abbreviations that you will use during the study of activation analysis. These are some abbreviations. Last time you have studied all these. And so other thing that is very important, the rate of growth of the activity is expressed by this term, change of the rate of change of number of atoms present in a sample material is related to the lambda n. So lambda is the decay constant of a produced activated product. And if we integrate it with the help of some limits, t is not to p, and like that, so we will get equation, this equation, okay, okay, this equation. So this actually gives you the number of activated atoms at a particular time t. and it may be related with this equation. And if we simplify this equation, it will get you will get lambda. If we shift to lambda from this side to left side, then this actually appear as an activity. So the number of decay constant and the number of atom at some time t, these are the activated atom that have ability to uh, radiate uh, emit the radiations. So this is called the activity. So activity mean how much element atom actually have ability to emit the radioactivity. So this is called activity. So this equation actually you may find here. And again, this factor is called the saturation activity. Saturation activity mean the particular activity, highest activity that is acquired, that is we obtained after the bombardment of a neutron or any other particle which have ability to activate the sample material. And this term is known as frequently called saturation factor. So saturation activity and saturation factor both are the different um, terms. It is activity that relates to the radiation, and it is a factor that compensate the different process regarding the time, regarding the flux of the neutron that is being bombarded over the particular time. So this is just like a factor to compensate the activity. So it should be noted that irradiation for one half life produces 50% saturation. So I think you should be very careful about some particular aspects and particular facts that should be in your mind. And so this is a first fact that you can say that it should be noted that irradiation of one half life produce 50% saturation. Uh, if we You can say that if we irradiate a sample material, okay, for one half life, if a component or a product or a sample material have half life of about 6 hours, and you irradiate it with 3 hours, for 3 hours, then it would produce 50% saturation. 50% saturation means there is a 50% activation of the sample components, while irradiation for 4 hours, four half-lives, about 24 hours, if there is a half-life is 6 hours, then it gives on 94% saturation. So in this regard, you would be able to easily calculate in first half, only 3 hours 50%, and rest of the 21 hours 94% saturation is obtained. So you can say that this is a big difference when there is a difference very going to very narrow from the highest activity. So then after the passage of time, time is going to pass more and more, but the change in the saturation is very slow and but steady. So this is the maximum activity that we obtained after 4 half-lives irradiation of a component material. The saturation factor is plotted as a function of time. Yes, definitely saturation factor mean factor when we discuss, when we talk about the factor that is definitely it is about 0 to 1. And definitely when we uh, irradiate the sample material like that here as discussed, 4 half-lives irradiation give a 94% saturation. So saturation factor also going to increase near to the 1. So as it is represented here in this is a ratio irradiation time, and so time irradiation, and this is saturation factor as time is passes, and the saturation factor also going to near to 1. So we can say that it is generally not worthwhile to irradiate a sample for a period exceeding 5 or 6 half-lives. So it is a very wise thinking that if you want to irradiate some kind of sample material in order to activate it, so it should be keep in your mind that that should not be irradiated more than 5 to 6 hours. As maximum, you can say that after 4 half-lives you get 94%. So if you further irradiate it with further 5 hour, further 6 hour, and then further another 6 hours, so 12 hour you passes, but your activity saturation activity will be increased to only 95 to 96. So if you say that you would be able to get 100%, it would never be possible, because whenever you are going to irradiate, the sample material that you are actually obtained is a activated product, and this activated product constantly decayed all as well. So production and decay also the similar, you can say that a parallel process there. So if there is, you want to get some 100% activity, but there is some of the activity you obtain that will be disappeared during the decay process. So it is very wise thinking, you should not go ahead from 4 to 5 half lives. So where T less than 1.5 half-life, an error of less than 5% is introduced by simplifying FVM. Okay, this is another fact. This is very important fact, because all these facts you should you should keep in your mind that fact is very important. Fact actually give you the idea, give you the baseline of your study. So facts should be in your mind. Oh, so these are also very important with respect to the multiple choice questions as well. So if we nullify, is if we just simplify this equation, so this equation appear into as AT, activity at a particular time, is equal to saturation factor lambda t. So lambda t, because this is a factor near to 1, so our just you can say that by simplifying this equation, this part of this factor that is called saturation factor, that would be equal to lambda t simply. Okay, now by inserting Avogadro's number, the weight of the desired element, the isotopic abundance, and the atomic weight in equation 4, the latter can be written as. So you can easily mention here, this is equation. You can put all the different kind of values in this equation, and this equation will give you the idea about the further how much activity will be produced there, because activity is related with the abundance of the element. So abundance of element give you idea how much activity we can obtain from this type of element. So W into isotopic abundance into Avogadro number over mass give you the another activity. How much activity will be produced through this. This gives you the exact number of a particular type of isotope that is actually radioactive. The decay of uh, activity must also be taken into account. And definitely, as I have discussed in previous slide, if you want to go, want to obtain 100% activity, it is not possible, because decay of activity is a parallel process with the production of activity. So, if there is a decay process, if there is a production of activity, production of radioactive material, so at the same time, there is also some of the radioactive material will be decayed into some stable isotopes. So, it should be in your mind while accounting, by considering and while calculating the activity of a particular type of a radioisotope. So must be into the account. The decay obeys the relation. So this decay actually obeys this relation, and this relation will give you exact idea how much activity actually behind in your hand after production as well as decay of the produced material. So where T-bar denotes the time interval between the end of the irradiation and the time of measurements. So when you complete the bombardment, and after completion of the bombardment, after 6 days, you actually want to measure the activity. So during these 6 days, there is a lot of component, lot of radioactive material have not been decayed. So you should have to take an account all these decayed element as well. And the ratio, and this ratio is T. This is the interval of bombardment finishing as well as the measurement of the radioactive material divided by the half-life of that material. As will be shown later, decay during the sample transfer can be a significant factor in activation analysis. So as will be shown later, a decay during the sample transfer can be a significant factor in activation analysis. Definitely, you should know, because if there is a lot of component that you have produced activated during the activation analysis, and you want to measure how much activity is there, and activity shows that there is about you can say that 40%, but when it was produced during the activation, that was 60%, then 20% was actually disappeared due to the decay process. So when actually you are going to analyze some kind of sample material quantitatively, then you should have to take uh, extra care in order to calculate how much activity have been decayed during the shifting process from reactor to the measurement lab. So this is a very important factor that should be in your mind while calculating any other thing. So this is a sample example of the calculation of components. This is just like an assignment, and it is that notes I have given you, share with you. On that notes, there is a page number 53. You should calculate it. Okay. Next is the about the neutron. So you should know about what type of neutron actually we use in order to activate the analysis process, activation analysis process. As I have discussed with you, there are three main kind of neutron. One is the main. There are two type of neutron. One is the fast, and other is the thermal neutron. And most probably thermal neutron are being used in order to activation process. What are the reason in order to measure, in order to use the thermal neutron? And so we study here in this screen. Neutron capture with the release of a gamma ray has a relatively high probability for slow neutron. Definitely there, if there the neutron is as have a slow motion, it have greater impact over the production of gamma radiation from activated products. So this probability is frequently inversely proportional to the high velocity of the neutron. So what are the thermal neutron? Uh, there should be neutron with the most probable velocity of 2.2 into 10 raised to 5 centimeter per second in a max billion distribution at 20 degrees centigrade are called thermal neutron. So this is a packed definition of a thermal neutron, so which is related to the velocity as well as energy at some particular type of temperature. So these are actually called the thermal neutron. These a thermal neutron, how these are produced, this is another very interesting way, because the neutron that actually produce during the fission process or any other process, these are actually fast neutron, but they are slowed down in order to make them a thermal neutron. So thermal neutron are obtained by exposing fast neutron to moderating material such as water and paraffin. So paraffin and the water are the moderator material. If the thermal neutron are exposed to these two materials, the neutron we obtain become slow and with less energy. So these neutron actually called the thermal neutron and are very good in order to use during the activation process. So there is in previous chapters, there is a table 2.5 lists thermal and fast neutron fluxes of some of the more commonly encountered sources of a neutron. Similarly, there is appendix D that I have provided you during by group. So there also have a maximum data was produced about the thermal neutron and their production and abundance like that. So you can consult these different data about the different isotope and their activation process there easily, inshallah. So time selective activation, at times selective activation by resonance neutrons can be achieved by the use of filters such as cadmium and boron, thus resulting in appreciable enhancement of one villa activity over other. So this is another important. You know what mean by the resonance. Resonance actually the coherence of the energies of two different materials. If the energy of one material is exactly matches the energy of other material, resonance is produced. So such type of a neutron having this property can be used, can be obtained by using some sort of filter of cadmium and boron, thus resulting in appreciable enhancement of one activity over the other. So this is an example of the use of a resonance neutron will be given subsequent in connection with the determination of manganese in biological material. So the main use of these resonance materials and such type of material neutrons actually we use in determination of the manganese in biological materials. Okay. So other are the factor about the neutron that should be in your mind. Many of the lighter element have low neutron to gamma activation cross section. So it should be in mind there is a two type of elements. One having the greater cross sectional area and other have less cross sectional area. So in both ways, those who have less cross-sectional area and short-lived activation products, whereas the cross-section of for fast neutron activation, that is NP, these are the nuclear reaction types. These are neutron is bombarded over the your sample material, and during the product, proton is released. Similar type of neutron bombardment, alpha these and neutron bombardment and neutron were these are relatively high for the high element. So these processes actually appear in that element which are in higher atomic masses, but these in which the low cross section in which only the n over lambda gamma activation processes occur. As in first second lecture of activation analysis, I discussed with you about the fact there are two type of gamma spectra in activation analysis we study. One is you can say that the prompt, and other is the delayed gamma spectroscopy. So prompt is associated with the short-lived radioisotopes, as you know, and the delayed gamma is associated with the long-lived radioisotopes. So long-lived radioisotope first of all produce beta radiation and some type of alpha radiation and neutron. And in accompanied in order to produce such type of particle material, they also produce in order to further stabilize, they produce gamma radiation that fall into the delayed spectroscopy, and we measure in our for the analysis of that element. Okay. Fast neutron activation frequently requires neutron with energies near 14 mega electron volt. But in case of slow moving thermal neutron bearing very less energy in order to activate the sample material. However, fast moving neutron is very difficult to obtain in continuous manner and at a very huge amount. So such neutron are not readily available in copious amount in many reactors, but are produced in good yield in Van de Graaff and Cockcroft Walton accelerator. So this is the accelerator. Accelerator mean you actually charge material accelerate in an accelerator under the electromagnetic field, and that after obtaining a particular velocity of that charged particles, you bombarded over some material that produce a neutron. These neutron actually fast moving neutron and continuously we can obtain. So it is difficult to establish accelerator at each um, analytical point where you want to analyze some sample material. So table 2.5 includes data on accelerators. That accelerator produce neutron. You can consult in table 2.5. If you have not, then let me, I will share with you. Use of moderator materials such as water or paraffin around the target assembly extend the usefulness of accelerator to thermal neutron activation. Okay. Other is Fig 2.6 and 2.7 shows a neutron generator at its installation for fast neutron activation. Similarly, figure 4.3. This is a figure 4.3. There you are seeing here there is some sort of these are the sodium, chromium, manganese. So these are different kind of element. These are if we see about this element that are can be determined with the sensitivity of 10 part per million or better following 5 minutes fast neutron irradiation. So if a fast neutron irradiated, these are exposed to the fast neutron at about 5 minutes. So these are very sensitive, gives you very excellent result up to 10 ppm. Similar information with the sensitivity of 100 ppm is provided for thermal neutron. This is a figure. These are the elements, these are the isotopes that are very sensitive to thermal neutron. So if these have some sort of component or concentration in a sample material like that 100 ppm, so it will be detected with the help of thermal neutron. So both figures are based on an activation flux uh, of 1 into 10 to 9 neutron per centimeter square per second and a disintegration rate of 100 dpm. So these are the two constant factor in both categories, and this category shows use 10 ppm and this shows 100 ppm. So it means it is more sensitive, 10 times more sensitive as compared to thermal. And but in case of thermal neutron activation, there are more and more elements we can easily. However, these are very few elements that could be estimated, analyzed with the help of fast moving neutrons. So these are the some activation processes. How we activated the product. There is some steps. These we have studied previously as well, but I will discuss to some extent. First of all, investigation of the feasibility of the technique used using data in Appendix D and E, considering. So, what type of technique you can use during the analysis of that particular type of material? What is the feasibility? So, it is based on the data that is given in Appendix D and E that I have last time shared with you in WhatsApp group. So there are three main factors: a type of activation, sensitivity of technique, and interfering reactions. So what about this factor? It should be in your mind. What type of activation you would like to conduct, and what is the sensitivity of that particular type of activation and technique, and what type of interfering reaction may take place during this technique. So these three things you should be careful about and should keep in your mind in order to conduct some type of analysis using activation analysis. So other factor is availability of the activating source and radiation measuring devices. So it is very important. If you choose some sort of technique and there is no availability of activating source, yeah, like that neutron source is not possible with that, and also you don't have any devices to measure that radioactive material. So it is you can say that not possible for you to use such type of techniques. So definitely there should be a activating source and as well as the measuring devices. Cost of activation technique versus cost by non-nuclear techniques. So it should be in your mind either if you are going to consult, if you are going to analyze some sort of material using activation analysis, but you should be prior to that activation process, either there is a non-nuclear technique is possible or not. If not possible, then you should have to step toward the activation technique using a nuclear reactor. But I think if there is a technique possible and present, which is a non-nuclear, that you should adopt. Other after you are choosing, definitely you have chosen the activation analysis or nuclear activation analysis. Then there is a step to prepare the sample. So most of the time it is not a very difficult process to prepare the sample, because mainly the closing of a sample material into some sort of material for the bombardment. So if there is no such type of preparation is required with the actual component, sample component, for example, in order to make it in a solution form, slurry form, pure form, like that. So there is a not very big burden in order to do like that. Just you have to take the material that you would like to analyze and put into an aluminum, quartz, polyene, and polystyrene are commonly used containers. Keep in mind irradiation, temperature, chemical interferences of containers extra. Okay, dear students, this is irradiation process. So after that you should have to irradiate the sample material. This sample material, how much flux you would like to analyze, you would like to activate the process, that should be in your mind. And Other thing is the purification. After the activation, the next process is the purification process. So if analysis of by direct gamma spectroscopy is possible, transfer material to unirradiated counter container. If necessary, dissolve material, add inactive carrier, and purify using radiochemical techniques. As you have studied that there is a two type. One is a radiochemical technique, that is destructive technique, because during the radiochemical process you actually waste all the material, because your component have now get some chemical reaction, and only one so in this regard you can say that you would be able to get this process. So dear students, as a comparative measurement, so this is some reference and some like that. Okay, so dear students, I think this is now much better to uh, end this lecture at this point, and you should have to study all these factors very carefully so that we can get some conclusion in order to go ahead, because we should have to study much more applications and like that things. So next time, in next lecture, I would like to give you information about the factors like that errors in thermal neutron activation analysis. So these errors, I think you should have to study it's their self fast neutron reaction, and like these are the different errors. Okay, so these are the errors, and very easy. If you face any problem during this error study, you can consult with me. I would like to share discuss with you. Inshallah, we'll see you in next lecture. Allah Hafiz. Dear students, Khuda Hafiz.